Hey everyone, it's currently Sunday afternoon, but I'm feeling sick, so in case I'm not at school on Monday, I'm recording these videos for y'all. So these are the notes over harmonic motion. Alright, so harmonic motion is a special type of periodic motion. I guess we should define periodic motion. We've kind of done it already. Like, for example, an orbit. The path of the satellite repeats over and over again, or circular motion, or something rotating back and forth. If it's rotating at the same speed, that's a periodic motion, something that repeats itself over and over again. And harmonic motion is a special type of that. For example, a weight vibrating on a spring or swinging from a pendulum will follow harmonic motion. So the main ways we describe harmonic motion are the frequency and the period. So period is the time for one complete oscillation measured in seconds. Frequency is the reciprocal of that, the number of oscillations per second, measured in hertz, which is an inverse second. So, for example, let's say a suspended mass. Now, one thing I can't demo it here. For a complete oscillation, it's not enough for something, let's say this mass going up and down. Y'all can see this on my video. One oscillation would return to the starting point. So, like up and back down, that's an oscillation. Down and back up. Down and back up, that's another. Down and back up, that's another. Or in a pendulum, swinging from one side to the other is not an oscillation. It has to swing back to where it started. So if we count the oscillations, there would be 1, 2, 3, 4, so on. Anyway, the suspended mass takes 30 complete oscillations in 15 seconds. What are the period and frequency of the motion? Well, frequency is the number of cycles in a time period. So it's 30 in 15 seconds. That's 2 inverse seconds or 2 hertz. And then period is 1 over the frequency. So that's 1 over 2 inverse seconds, which is half a second. So this cycles back and forth 2 times per second, or a frequency of 2 hertz, and it takes half a second for each cycle. Now let me fix that. All right. So whenever something's in harmonic motion, the graph of position, velocity as an acceleration as a function of time are all going to be sinusoidal. They're all sine or cosine shaped as a function of time. So we know the behavior of cosine is cosine starts at 1, but with an initial slope of 0. In other words, something that starts from rest at an initial position you describe with cosine, whereas where a sine starts at 0, but it has a non-zero slope, sine would look like that. And sine, so you use sine if something's at the equilibrium, at the position where forces are equal to 0, and it's set in motion if it's given an initial velocity. So the functions we use to describe harmonic motion are a equals plus or minus. Again, so that depends upon if it starts on the right-hand side of equilibrium or the left-hand side of equilibrium. Cosine omega n times t. Or a equals plus or minus a sine omega n times t. And this omega n, it's called the natural angular frequency. It's 2 pi times f, so 2 pi times the frequency, or 2 pi divided by the period. And then the period of any of these graphs, say like to get from there to there, that's one period, or from there, that's one period, or from there, that's one period. That's the period of oscillation. Those of y'all familiar with calculus, you might know that, okay, if you want to get the velocity, you could differentiate this. You'd have to do the chain rule inside, but you wouldn't change the frequency of what's inside of the function. So what's the deal with omega? I'll make this loop. Nah. So omega n in this context is not a literal angular velocity, but a mathematical artifact. So the sine and cosine functions can be generated by revolving a point on a unit circle at a constant rate and projecting its x and y coordinates respectively. Here's one example of doing that, though they do kind of have to bend and show that, okay, when this is over here, that's right there. And the equilibrium, that's right there. But here's another video that projects it like that. So we can see, let me pause right here. This y coordinate is the sine at that time, and this x coordinate is the value of cosine at that time. It's just shifted sideways. But omega n is the velocity of this imaginary point. And you can see that this goes through 2 pi radians in the time of 1 period. All right, so displacement. An oscillating spring will move back and forth the same distance from the equilibrium position. That's x equals 0 where the spring is relaxed. Or for a vertical spring, equilibrium is where the net force equals 0. So if you have a spring hanging, like in that first example we saw, that would be where the spring force would equal the force of gravity, and it would oscillate the same distance to the left or right of that point. And a spring has a maximum displacement to the left or right called the amplitude at each endpoint. So the largest for a spring on a horizontal surface, the largest positive value is plus A, the largest negative value is minus A. Though if this were a hanging spring, you just shift that by the distance where the spring force equals the weight. All right, velocity is the slope of the x of time function. So you'd use x equals minus or plus the maximum velocity times the sine of omega t if released from rest. This is because sine starts at 0 at t equals 0. Or you'd use x equals plus or minus the maximum velocity times cosine of omega nt if it's given an initial velocity from equilibrium, because here cosine starts at x equal or starts at a non-zero value. So if it starts with a velocity, you want to use cosine for the velocity. And velocity is positive when moving to the right and negative when moving to the left, the same as we've already seen. And it's 0 at either of the endpoints and at a maximum at the midpoint or equilibrium right here. So at this point, the speed is maximized. It'll either be plus Vmax if it's moving to the right or negative Vmax if it's moving to the left, where Vmax is omega n times A. Again, those of y'all that know calculus, you can see where that omega n out front comes from doing the chain rule with what's inside. Then the acceleration is the derivative or slope of a of t. It's also sinusoidal. It'd be minus or plus cosine omega n times t if released from rest. Because if you release it from rest, that's, say, over here, this is where the spring is at its most stretched. So it'll start off with the largest possible force on it. So it'll initially have the largest possible acceleration. But if you start it off to the right-hand side of 0, it'll initially accelerate to the left. And if you start off to the left-hand side of 0, it'll initially be pushed to the right. That's why our position function was plus or minus. This is the reverse, minus or plus. So acceleration is in the direction of the spring force. It's positive when x is negative and negative when x is positive. Now, if the object's given an initial velocity at equilibrium, we want to use sine because sine starts at 0, and at equilibrium, this is where the forces are balanced. So at least for an instant, the acceleration would be 0, too. So acceleration is maximum at the endpoints and 0 at the center, and the maximum acceleration is omega n squared times a. All right. For a mass vibrating on a spring, its period is equal to 2 pi times the square root of the mass divided by the spring constant, and the frequency is the reciprocal of that, 1 over 2 pi times the square root of the spring constant divided by the mass. So notice that a stiffer spring, if you have a larger value of k, that'll create faster vibrations, whereas, or a shorter period. But the inertia of the object, a heavier mass, ends up creating a longer period or slower vibrations. Interesting fact, though, in College Board will probably ask you about this some way on a multiple choice. The gravitational field and the amplitude of oscillation have no effect on the period and frequency. Provided this is a normal linear spring, it doesn't matter how much you stretch it before you let it go. It'll take the same amount of time to go to one way and then back to the other. It may have a further distance to travel, but it's also, with starting off with a more stretched spring, it'll have a greater acceleration and then reach the middle. So it'll be going faster when it reaches the middle. And again, it'll be faster going back the other way. So it may travel a greater distance with a larger amplitude, but it's going faster too. Also, gravity doesn't matter, not even for a vertical spring. There'll be a question about, okay, what if you did this setup on another planet? How would the frequency change? For a spring, it wouldn't. So let's say we have a frictionless system that has 2 kilograms of mass attached to a spring with spring constant 400 newtons per meter. The mass is displaced a distance 20 centimeters to the right and released. What are the initial acceleration and frequency of the motion? Well, for the acceleration, we could use that a or that minus omega squared a sine blah 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 or cosine, but it's just as easy to use Newton's laws. This thing, its acceleration in the x direction horizontally is equal to the sum of the forces in the x direction divided by the mass. Or if it's pulled to the right, the spring force will be acting. If it's moved to the right, the spring force will try to pull it to the left. So we have the negative of the spring force divided by mass. Spring force is k times x. So we have negative spring constant times the displacement divided by the mass, or negative 400 newtons per meter times 0.2 meters divided by 2 kilograms, which works out to negative 40 meters per second squared, or 40 meters per second squared to the left. Then for the frequency, well, I'm actually going to solve for the period because the equation for frequency is not on your formula chart, and instead of making you memorize it, let's just use the equation for period, which is on the formula chart. The period of a spring is 2 pi times the square root of mass over spring constant. That's 2 pi times the square root of 2 kilograms over 400 newtons per meter, which would be 0.444 seconds. You can show it on your own, but somehow kilograms divided by newtons per meter square rooted works out to seconds. And then the frequency would be 1 over that, or 2.25 hertz. All right, for a pendulum, pendulums follow the exact same rules concerning velocity and acceleration at the middle and endpoints, provided the maximum angle is less than 15 degrees. to get what we call simple harmonic motion, we have to do something called a small angle approximation. We'll actually derive this and prove it mathematically in Physics C next year. But the math only works out, and this is only approximately true, and you only get a good approximation provided the angle is 15 from vertical is 15 degrees or less. So you want to use theta equals plus or minus a cosine omega nt if released from rest at the endpoint, or the angle theta equals plus or minus a sine omega nt if given an initial velocity at the equilibrium. And follows the same behavior. The maximum velocity will be at the middle, and it's got zero velocity at the endpoints. The maximum acceleration will be at the endpoints, and it's got zero acceleration down at the middle where it's in equilibrium. All right. So the period and frequency of a simple pendulum are given by period is, again, we have a 2 pi times the square root of length divided by the gravitational field. And then frequency is the reciprocal of that, 1 over 2 pi times the square root of gravitational field divided by length. Now note, the mass of the pendulum and the amplitude of oscillation have no effect on the period and frequency of the oscillation. Again, provided we stay less than 15 degrees from vertical. It doesn't matter whether you release it at 1 degree or from 10 degrees, it'll have the same period. Because when it's tilted more, there's more restoring torque to accelerate it back towards the middle. It has to travel through a larger angle, but it'll have a greater acceleration while doing so, and a faster average speed. And the mass doesn't matter. Again, we'll prove why this is in Physics C, but basically it works out because you have the gravitational force, which drives it, which is proportional to m, but then the inertia that resists it is also proportional to m. So it's similar to how a lot of problems with something falling through the air or sliding down a path, the mass of the object doesn't matter in the final result. All right, here's an example. Pendulums are often used for timekeeping, like say in a clock. What must be the length of a simple pendulum for a clock which has a period of 1 second? So we want it to go from one side and back. We want that to take 1 second. 1001, 1002, so on. So the period of a pendulum is 2 pi times the square root of length divided by gravity. We plug in what we know. 1 second is equal to 2 pi times the square root of length divided by 10 meters per second squared. We divide 1 second by 2 pi. When you're doing this on your calculator, make sure you put 2 pi in parentheses, or your calculator will interpret it as 1 over 2 times pi. So we get 0.159 seconds approximately. It's an irrational number thanks to the pi. Equals the square root of L over 10. Square both sides, and we get 0.0253 seconds squared equals L over 10 meters per second squared. Multiply both sides by 10, we get 0.253 meters equals the length needed. It'll be a little less in the real world because gravity is actually 9.8, but 10's good enough for this. All right. Since springs and gravity conserve energy, they're both example of conservative forces. The total mechanical energy of a system in harmonic motion is constant unless something like friction on a rough surface that the mass is sliding back and forth on, or if there's significant air resistance that it's oscillating through, dissipates energy over time. Pendulums and springs have maximum potential energy at the endpoints. That's either where the pendulum bob is highest, the greatest height, or where the spring is at its most stretched or compressed, and they have maximum kinetic energy in the middle. And they've got zero kinetic energy at the endpoints. That's where they're temporarily at rest. And depending upon what you define zero to be, they'll usually have zero potential energy at the bottom. Now, one thing to keep in mind, and we saw this already in our energy unit, but just a refresher, the height of a pendulum for the purposes of energy calculations can be found with a little geometry. Let's say a pendulum starts at an angle theta compared to its lowest point, that height above it. Well, this length here is L. This length right here is also L. And if we draw a right triangle over here, we can see that this segment here would be L cosine theta. So its height above its minimum height would be L minus L cosine theta, or L times 1 minus cosine theta. All right, that's the notes over harmonic motion. Now there's a homework on AP Classroom, and I'll also be making another video going over the AP free response questions, but hopefully y'all end up not even seeing this because I'll be in school Monday. But if not, then remember you can sign up for DIN sometime or come in before school and ask. Before school is the best time to find me.